Thank you, and thanks for the opportunity to present here. So, as was said, my name is Edward O'Dwyer. I'm a research associate at Imperial College London, and I'll be presenting today some of the work that we've been doing as part of a Horizon 2020 funded smart cities project called Sharing Cities. So we've been working specifically more on the smart energy aspects of it, so smart energy in an urban landscape. So, So I'll start just talking about the context. What do we mean when we say smart energy in an urban context? What are the opportunities and what are the challenges? Following that, I'll talk a little bit more about the actual, the objectives of the project itself. Focusing in a little bit more, I'll look at the London aspects of this project. So it's a European-wide project, so there's several cities involved. London is one of the cities. Greenwich in London is where some of the interventions are taking place. So it's about working with the councils, working with the Greater London Authority to introduce these innovative solutions. Following that, I'll briefly talk about SIMS. So that's the energy management system that we're developing as part of this project. So that's the point of the system is to coordinate the different energy assets. And I'll talk about some of the challenges with that. And following that, I'll talk about the real kind of meat of what the paper was that I'm presenting on, which is the modeling framework that you can use to design these urban energy systems, given that they're now controlled in more intelligent manners than before. I'll then show very briefly some case studies. So in terms of context, what do we mean when we talk about urban energy and what are the real opportunities here? So in like an aspirational, idealized case, we can see this as this kind of ecosystem of assets with end users and suppliers all operating in unison to provide like globally beneficial system performance. So that might mean better in terms of financial performance, better in terms of environmental performance, better for fuel poverty, better for air quality. There's all these different objectives, but that's a little hypothetical because the problem itself is really complicated. You've got different technologies, you've got different levels of stakeholders between government bodies, the national grid, the energy users themselves, the people who, let's say SMEs who own smart sensor companies. So it's really only intelligent and it's really only smart, and you can really only consider it a smart urban energy system if these assets can collaborate in some way that's actually beneficial for everybody. And furthermore, because this is a complicated problem now, it's more complicated than it would have been before, where all these actors would have been acting in silos, the design of these systems is now a little bit different, and the design is also very contextualized. So what I mean by that is that, as with any urban challenge, there isn't any silver bullet. There's no one single solution that will work for every city. Many reasons for that. I've put some of them in boxes here. You've got different levels of resources available. You've got different policies, different pricing structures for energy types. You've got different mixes of stakeholders, and certain technology preferences are there. If you're in Scandinavia, for example, you'll have district heating, as that's very common, whereas in many other countries it's not. And following that, there's also cultural impacts. And again, Scandinavia, because of these district heating networks, they're quite used to these communal energy systems. So you can talk in terms of system-wide interventions that benefit everybody, whereas that's a lot more difficult to introduce into places that aren't used to that. So then you've got subsidies and taxes as well. It's different everywhere. So you need to think about all these different considerations whenever you're designing these problems. Which brings me to the Sharing Cities project itself. So it's a 25 million project. It's quite large. So I'm not going to give the overview of the whole thing because it's a typical Horizon project where there's many threads. The purpose of it is to set up 3 lead cities as kind of pilot cities where they can act as proving grounds for certain technologies that are becoming new. There are 3 follower cities then which try to take these innovative solutions and apply them to their own contexts. So the 3 lead cities, it's London, Lisbon, and Milan, are the main focus of this, and the purpose is to, well, I guess, to provide a better common approach to making smart cities a reality. That's the blurb. But it's all about working with councils, working with different actors involved, and working with the actual end users themselves to come up with something that, well, everybody's happy with. The consortium is pretty big. There's cities and public bodies, there's NGOs, there's industrial partners, a lot of them, and there's different academic institutions. So we're just one small part. The London side of this project, as I say, it's taking place in Greenwich. So Greenwich, it's down in the southeast of London, and they're doing quite a lot of good stuff there, and they've got quite a lot of good plans, so this project fits in nicely with what they're doing. There's various interventions such as smart parking bays, electric bikes, and they're also introducing a lot more electric vehicles, like a lot of other cities are doing. And they're trying to exploit the River Thames as a source of heat. So it's a common, we're seeing it more and more now that as people are trying to decarbonize their energy systems, the two of the main approaches that are taken are to electrify transport and to electrify heating. So if you electrify heating, we're kind of talking about heat pumps. They're looked at as being quite a potentially impactful way of doing that. And so Greenwich are looking at using the Thames to provide heat for heat pumps to heat the social housing within the district. Further to that, they're also introducing some renewables, that's some PV, and smart lampposts and different things to allow users to interact with these systems. So drilling down a little bit deeper, just to give you an example of one of these interventions and the kind of stuff that they're doing. So this is the Ernest Dents estate. It's a social housing complex with 95 flats. It's built in the 1970s, I think, but they're planning this deep retrofit, and they're planning on putting in proper monitoring systems in the heating systems and putting in demand response and managing this with using this energy management system. So it should act as a useful actor within this energy ecosystem rather than being just a drain on energy, and a poor performing one at that. The existing situation is it's not performing very well as things stand, which means that there's a bad baseline, which is kind of good for research. Anything we do will be great. But there's 3 gas boilers which are operated continuously, and there's no monitoring, pretty much no monitoring. There's no control that the users have of these radiators, so if the system is on, it's on. The control that they use, you can see if you walk past the apartment complex, is that the windows are always open. So if you want to cool down your flat, you just open the window. The radiator still runs. So it's quite poor, and as a result, you end up with a really high annual energy cost, and you end up with a really high emission rate associated with that. There's also air quality issues if you've got these old boilers running in this kind of urban setting. So what they're doing, they've got some different interventions that they're planning to put in place. They're doing the typical things such as roof insulation and wall insulation, replacing windows and lighting. They're also replacing the heat network, which is what we're a little bit more interested in, with a low temperature heat network with heat interface units that allow the heat pump taking heat from the Thames to deliver heat to the apartments at a great reduction of carbon. And they're reconfiguring the full secondary side of the heating circuit, so you're getting a lot of savings there. So that's one of the main kind of focuses of what their work is. But just the wider Greenwich system that we're kind of looking at, as well as that Ernest Dents estate, which is in the middle. You've also got PV generation. You've got the heating network, which is, instead of these old boilers, they're now going to have heat pumps, as I say, as well as some thermal storage. So thermal storage is great. You get flexibility that allows you to coordinate things. So you can use the store as a form of flexibility. As well as that, they've got new EV charge points. They've got some e-bikes, some smart lampposts, and the entire thing should be managed by this smart energy management system, which takes forecasts and pricing information and uses various types of intelligence, some machine learning and model predictive control, and new intelligence techniques to provide, the solution that works best for everybody. So yeah, this is what this energy management system is. This is one of the main remits of the project, is to develop this. So if you've got heat networks and you've got EVs, you can kind of manage the whole thing in a way that if you've got a spike predicted for your EV usage, you can offset that by using the flexibility in your thermal network. So in theory, this is all pretty good. That should work quite well. Again, this is the kind of typical graph that would get shown. I'd say this is the renewable generation in an area. It might follow this curve, so maybe if you've got a lot of solar, then when the sun is up, then you're getting the most. Meanwhile, the demand curve looks maybe something a little bit more like this, where you're getting more demand for power when people need lighting, and it can look something like this. This is just representative. But the point is that there's a mismatch between when you're producing the renewables and when you're consuming power. So the idea is that, okay, look, if you've got storage, if you've got flexible set points, then you can shift the demand. If you've got demand response, you can do all these things, and you can store energy. So you can kind of delay the demand, and you can delay when you're using the generation. So that's one side of it, but also as well as that, with this energy management system, you want to be able to exploit different changes in pricing to allow you to get cheaper energy. You want to be able to exploit changes in the grid emissions, so you can get reduced CO2. And you want to be able to do it in a way that, and this is one of the most important bits, that peaks don't completely screw your electricity network. It's a big thing if you're electrifying everything. That's a massive strain on the current power network, and retrofitting all this infrastructure, it costs an absolute fortune. So if you can find ways to reduce the need to increase the capacity of these power networks, then it's really worthwhile. So in theory, that all makes sense. In theory, that's fine. But it's a really complex system, so there's a lot of decision variables here, and it's a difficult optimization problem where you need to think about actors at different levels. So as I was saying, you've got SMEs, you've got end users, you've got governments, you've got everybody involved in the system will have their own way of looking at it. A lot of these objectives will conflict. So if you're an energy company and you're trying to sell people as much energy as you can to make as much money as you can, obviously your objective is a little bit different to if you're an end user trying to reduce the amount of energy you're using as much as you can. So, yeah. There's a couple of aspects to this. When we say the optimal solution, so if we've got an energy management system that's providing these optimal set points to all your assets, I'm putting optimal in quotations here because first of all, you need to think about how it's determined, how it's enacted. So these are technical issues. Okay, they're not so interesting for here, but there's a lot of interesting research in that. But possibly more important, we're kind of wondering, what does optimal mean? When we say, okay, we can reduce the cost of the fuel cost and we can reduce the environmental impact, these things might not necessarily complement each other. There might be a conflict there. How do you balance these objectives? How do you prioritize these objectives? Optimal for who? That's a very important aspect of this. If you've got this energy management system, which let's say the council in Greenwich, for example, want people to interact with, the more people that interact, the better, the more flexibility you have. But why should they interact with this system? What's in it for them? You need there to be an incentive for everybody involved. That's, again, you're going to be left with conflicting objectives between the different actors in this ecosystem. So who is determining what the optimal solution is? And furthermore, how can you balance these competing objectives? As I said before, you've got financial efficiency, fuel poverty, and environmental goals. Like fuel poverty can be quite an important one, particularly for councils. It's one of their main objectives is that you're not managing these systems in a way that somebody could buy a battery because they've got the money to buy a battery and exploit this more, whereas someone who can't afford a battery can't exploit this, so doesn't get the benefit. So how do you do it all fairly? It's quite difficult. And from so the first 2 points were kind of more technical, and this is sort of how the technical side of it looks. It's kind of a classic diagram that I'd kind of show about when I'm giving more presentations about what's actually under the hood of the SIMS algorithm, but it's basically you're taking measurements from the system. You've got wireless sensor networks everywhere. You're gathering all this data, you're putting it into this brain, which is this mix of machine learning algorithms, optimization algorithms, some model predictive control, and you're spitting out some set points that you send back to the controllers. The point is that you're not actuating at the low level. That's kept separate for the sake of robustness. If something happens here, you don't want the whole system to break. So you're kind of operating on the mid-level and at the high level. At maybe 10 or 15 minute intervals, you're sending new set points. Maybe predicting operation for a day ahead, that kind of time scale. In a more detailed manner, this is what our specific solution is for the Greenwich case. And I don't really want to talk too much about it just because it's not that relevant to what I'm saying, because this is really a specific solution for a specific case where you have thermal demands, you've got electrical demands. And we've kind of split the problem into the heat network problem and the EV PV network problem. We've got a layer of MPC which delivers set points for all the assets with the heat network problem, and we've got another MPC which delivers set points to the EV PV problem. And we've got a coordination layer, so if we're predicting that the overall system is going to get overstressed, then we can rejig how the optimization on the lower layer is carried out. But the reason I don't want to go too much into that is because I guess essentially all of this kind of is part of this brain, right? And what is important to consider here is that as much as I might use a slide like this where it's just this mystical brain, that's not actually that useful. If we're dealing with councils and we're dealing with residents and we're dealing with people who actually want to get benefit out of this, cloaking all of this in this mysterious intelligence layer, which is like this magical box that gives you the best answer to every problem you've got, that's not really very useful. Because, as I said before, how you design these algorithms, so how you kind of weight the different objectives, that's very important as to how the system will operate. So how the design of this system will be affected by these decisions is very important to consider. And if you just consider it as a magical box, well, then it's not really very useful for anybody. So we need to think about it a little bit more. How do you kind of communicate these issues? So it's a complex design question now because you've got all these assets. You've now got this added intelligence bit, which has its own parameters associated with it, and you want to be able to design the technologies for the context and the intelligence for the technologies for the context in a way that actually works for everybody. So quantifying that is kind of necessary. You can't just deal with it as here are these arbitrary weights that we're dealing with. It needs to be in real terms. It needs to be in pounds. It needs to be in tons of CO2. And we need to think about how the operational approaches can be mapped to the different stakeholders to avoid in certain stakeholders getting all the benefits and others not getting any of the benefits. So for that, we need modeling, and we need possibly new levels of detail in the models that would typically have been used before, because we have a lot of scope in terms of the number of systems that we're dealing with. All these systems interconnect. The more you grow your energy system, like in your energy management system, the more systems you're going to have interacting with each other. How do you capture all these systems in one modeling platform? But you still need the detail to be able to consider these operational kind of 10-minute changes that will really underpin the entire performance of the system. So you also need to be able to capture the intelligence behind the actual operation of the system within this modeling platform. So this kind of leads to talk about digital twins, which I'm going to use the term in a very careful manner because I'm not, I think different people have views on what exactly it is, and I think a lot of people with CSIC here are doing some really good stuff in nailing down exactly what is a digital twin, what isn't a digital twin, so I'm going to be careful so I don't say anything wrong. But we can think about it as it's another way in which a digital twin is really useful. If you've got a virtual representation of your system, which, okay, let's say it's working online, let's say it's working in tandem with your real system, well then you can see what happens with different operational decisions. You can see if you change your intelligence, if you re-weight your objectives, you can straight away see what the impact on the system is in the terms you want. So in terms of pounds, in terms of tons of CO2, in ways that can be understood by councils and by residents, by everybody, which you just can't really do if you don't have this detailed model available to you. So it gives you a deeper insight. It allows you to see if something's maybe going wrong. As these systems get more complicated, the worst thing that could happen would be maybe some kind of a cascade failure where one system breaks and the whole thing falls over. So you can it's becoming more and more important to be able to detect these kind of anomalies offline. Or online. So that's the online aspect. So where I'm okay in calling that a digital twin. The offline bit is, I'm not really sure. But prior to the development of your system, you also need to think about the design challenge. So as I say, and as I've reiterated several times, obviously the design is impacted by the intelligence. So you need to be able to actually do some simulation work. You need to be able to do some sensitivity analysis on the different parameters of that to see what will work better before you actually install these things. Maybe a massive thermal store will work for one person, maybe it will not work for somebody else. So it allows you to do this design and analysis. Now, what that means is it's prior to the development of the actual real infrastructure, so it's some kind of digital only child, I don't know. I'm just gonna call it a digital twin because it's easier, but it allows you to do apples versus apples rather than saying apples versus oranges for these things. You can really kind of quantify what's going on. So that was the approach we decided to take. In the real world, this is what we want to end up with. We want our SEMs integrating with our real sites via, it used to be this was an old slide, but the urban sharing platform, I think it was initially called, but now we're just going to use the London data store instead because it's there and it's really good, so why not? But as is the case with these kind of projects, the development of this actual infrastructure, it's very slow. So prior to that, we need to think about how we design the algorithm, but also, and another factor which I haven't really mentioned yet, is there's this integration layer. So this integration layer for this project is being developed by Siemens, and it's not necessarily straightforward how you do this, how you communicate all these sensors to a central platform. That's not an easy problem. And being able to do that in silicon is very useful, so it allows you to make your mistakes in silicon. So you're not doing something that just won't work, or it just won't be able to operate at the timescale you want it to. You'll have lags maybe that you don't want. You'll have dropouts that you don't want. So that was the approach we decided to take. Because we've got this delay before the real world case happens, let's do a proper job. Let's develop a digital twin of the system that can mimic the real world as best we can. We can design our interface layers. We can design our intelligence algorithms in a way that is understandable to councils, residents, everybody. So, yeah, quickly I'll go through this. What the purpose of the simulation environment under it is, it's, okay, again, you want to be able to test different control strategies, different designs, and you want to do some sensitivity analysis. So some of the challenges, which are probably more interesting, well, first of all, is it valid? So how do you kind of get it to match measured data if the systems don't exist yet? Adaptability and scalability, that's really important. So the point of this project is a proving ground for technologies. We're not trying to do a single solution that works in one city. Obviously, solutions need to be designed for each individual city, but maybe the process as to how you evaluate these solutions can be common. So how you do a modeling framework that's adaptable and that's replicable. We initially were going to do everything in MATLAB because we're academics, that's what we find easiest to use, but it's not feasible to transfer that to everybody. There's always, if you need many people to use a technology, there's always going to be a link in the chain where a software license will be a problem. So we shifted everything to open source. The intelligence is all in Python. The modeling software I'll talk about in the next slide. We also need to think about what's the level of complexity you have. So you need it to be able to run and contain enough detail, but you also need it to be able to run sensitivity analyses, which might involve a lot of simulations. And granularity, same issue. And modularity. So can you just add new components without having to redevelop the entire thing? So the architecture we used, as I said, it was open source. So what we developed it in was, we used this Ptolemy 2 framework. So Ptolemy 2 was developed in Berkeley. It's pretty neat. It's kind of like some kind of MATLAB or Simulink, but it's open source. And it's got different packages that are built with Ptolemy 2. So one of which is the Building Controls Virtual Testbed, BCVTB, which is very useful for a co-simulation. So you can take different simulation packages, open source or not, it doesn't really matter, and you can run them concurrently. So that's why we use this, because central to our whole problem is this big building. So we use Energy Plus, which is again this like state-of-the-art energy modeling simulation software tool, which is again open source. And we use that within this Ptolemy 2 framework. We modeled everything else just in Ptolemy 2, so that's all the heating system components, all the EV components. We can add to it as it is. I say that because the EV components are now, they're just time series with distributions. We could add different ways of simulating these things. You could plug in an ABM or something like that. But the point is it's all put together in this block modular kind of fashion. That means that it's not just an overspecified single solution. Very important aspect to it is that the intelligence bit is kept separate. When we're designing the interfaces, or more specifically when Siemens are designing the interfaces between the intelligence and the real system, we kind of need to have them separate. So what the intelligence wants to see, or what the intelligence layer and the integration layer wants to see, is just signals that look exactly like the sensor signals from the real site. So that's what this produces. This produces sensor readings. We then send them via this web app framework, so we're using Flask to communicate with this SIMS, which we've got then on a web server. So that allows Siemens to say, okay, these two pieces are separate. We can now develop our bit in the middle. And when we put the two together, it should work. The intelligence should work with the integration layer, with the digital twin. And when it comes time, we can then, after we're happy with the integration layer and we're happy with the intelligence, we then just plug this out, plug in the real system, and everything should work. We'll see. Maybe it won't. I don't know. So that's essentially the solution we came up with. And we did some validation of that using the only system component that's already there. So that's the building, the pre-retrofit building. And the real data, which is in black, so there's a couple of dropouts, but it's pretty good. So this is measured with the Siemens Navigator API. And this is the total heat load of the building. Actually, no, it's the total gas consumption of the building. Not wrong. But, and the orange is the modeled version, and it's pretty good. The total error for the full, this is about 50 days, 56 days maybe. It's about 3% difference. That's really good. And more importantly, because it's always going to be a little different because you're making certain assumptions about the user behavior, it's capturing the trends that follow the weather, and it's capturing the kind of day-to-day heat load profiles pretty well. So then if we're happy with that model, we can then do some case studies with that model. We can look at what their retrofit is going to look like, so that we basically simulated all the changes that they're planning to make. And we were able to come out, okay, it works out. If you do this, again, this is the black is what the baseline model, the current situation, and the orange is the post-retrofit situation. And you save about 12% of energy if you do what they're planning to do. So it'll be interesting to see if that lines up with what actually happens. So that's without changing any of the heat networks, without adding the intelligence, without doing any of that. So then we talk about actually adding the heat networks, bringing in this electrification of heat, bringing in this intelligence layer that manages this, so it's able to either so as a start, just as a case study, it's either able to minimize the cost, so the operating cost, or it's able to minimize the operating CO2 emissions. And even though this is quite simple, and for a lot of you guys here, this will be quite obvious, it's kind of powerful being able to show people something, and people in the council in particular, just something so clearly as this. Because if I'm talking about, okay, you've got this multi-objective problem, how do you weight the objectives? It's much easier if you can just show a graph that says, okay, look, with the CO2 minimization, this blue is the CO2 you get. If you use the pound minimization, this blue is the CO2 you get. You get way more CO2 if you minimize pounds, but you get this extra cost if you try to minimize CO2. So you can straight away say, is this worth it to you? So this allows decision makers to say, well, is it worth it to us? And if we need a balance between the two, well, we can do that too. So inevitably, these multi-objectives will come out as these kind of Pareto curves where you can balance these different objectives and say, okay, how much energy saving is it worth saving a certain amount of money? How much is each ton of CO2 worth for you, or how much are you able to afford? How much comfort is a user willing to allow you use as flexibility for the wider system? You can quantify all these things very easily with this now. And you can then look at it from the design point of view. If you're putting in PVs, you can then say, okay, this kind of changes the design case than if you were going to put in PVs in a normal situation if you didn't have a heat pump running concurrently. Because if your heat pump is now the operating costs of your heat pump are higher because you're using this electricity from the grid. If you're able to use electricity from the PVs, then now you can come up with a situation where your total CO2 is much lower because you're using a heat pump and you're using PVs to generate the power for it as much as you can. And your energy cost is less because you're not buying as much from the grid. Now, that's a little better than if you were to just install the PVs and use the PVs just to sell to the grid. You might not be able to get this kind of combined performance. So then you'd be able to do sensitivities around this by saying, okay, how much PV is worthwhile? At what point are we just going to end up selling most of it to the grid? And you can do a proper intelligent design that allows this intelligence algorithm to operate in the way it's going to operate, and you can see what effect it's going to have. So just to end on some learnings, when we're talking about modeling and when we're talking about control and we're trying to scale up, over-specifying everything, it doesn't really work. So the modular approach is really necessary. We had a more specific approach, but there's no point because every case is going to be slightly different. So you need things to be scalable, otherwise nobody will have any interest. If you tell somebody you need to do it exactly like this, they won't do it. They'll do it their own way. The same applies to the control. If you try and tell people, okay, this is the forecasting algorithm we're using, they might not want to use that. Everybody wants to use their own. So you need to be you need to be allowed to use this kind of more plug and play approach. Underspecified is obviously not useful because it won't do anything. Modular approach is what you need for transferability and scalability. And yeah, just the main takeaway is that the wider system interactions, and in particular how these new intelligence algorithms can manage these wider system interactions, that can and should influence the design decisions. So that's just a summary of everything that we've done. I don't think there's anything really needed to go through with that. So thank you for listening, and just some of the main contributors, just to point them out, even though there's lots of contributors to the overall project for this particular bit. That's the GLA, the Borough of Greenwich, that's the council we're working with, that's Siemens who are doing the integration there, and us at Imperial College. So thank you for listening. Any questions, I'm happy to take them.